So this is the convex optimization part of the MPC course. And we'll be talking about optimization problems for 2 days, not specifically control problems, but just generically how to solve optimization problems and how to model them and what it means for a problem to be a convex problem. So before I start, maybe you can just show me with your hand how many of you have taken a course on optimization before? Okay. How many of you know what a convex function or set is? Oh, okay. Good. Okay. Well, that'd be easy. Oh, okay. Well, we're going to have an easy time. Okay. So I'm going to start off quite slowly, and just so that we're all on the same page, just define for you what it means to solve an optimization problem, and without reference to it being convex or not. And then towards the second half of today, we'll talk about what it means for a problem to be convex, and the different types of problems we might want to solve, and how we should go about modeling convex problems, and so on. And then tomorrow, we'll talk about duality and how to check whether a solution to an optimization problem is optimal or not, and when a problem is easy and when it's not. And the whole time, what we should keep in mind is that we want to solve these problems for control. And so most of the time, we'll talk about solving problems where we're optimizing over vectors in Rn. We won't worry about whether or not the solution to the problem exists or not, all of this stuff. Okay, I mean, we should just bear in mind that some of the things I'm saying are a little bit simplified, but for the purposes of control, or at least for predictive control, usually this doesn't matter. So if you notice at some point that I've written min instead of inf or something like this, and you have some objection, okay, I'm aware that there's an objection to this, but for the moment, we just gloss most of this over. Okay, so, right, so this is the outline. So we just give you a brief introduction on optimization and talk about what a convex set is, what a convex function is, and so on. And then tomorrow we'll do the, oops, yikes. Okay, this is going really wrong. Maybe doing iPad for the first time right now is not a good idea. Okay. Okay, so tomorrow we'll do the duality stuff, and maybe if we have time, we'll talk about the generalized inequalities, but the last step is not really essential for the course. Okay, so we start just with an introduction. So I guess most of you said that you'd seen an optimization course before, but not everyone. So maybe we should just start with what it means to optimize something, or what we mean when we say we want to solve an optimization problem, and why we should care. So when we solve an optimization problem, what we're saying is that we want to make some kind of decision about something, and we want to choose, in some sense, the best decision. And ideally, we would actually choose the best thing, but often we have some restriction on the type of thing that we can choose. That's, oops, yeah, okay. Maybe the pointer is not a good idea. We have this constraints here. We have some kind of restriction on the type of decision that we're allowed to make. And the particular way that we model the decision, or the particular thing that we want to optimize, and the particular constraints that we have are all completely problem specific. But what we find is that most of the time, the problems that we want to solve end up looking kind of similar across fields. So here's written a list of different places in which you find optimization. A lot of them have a kind of control flavor, but not all of them. So if we want, I won't talk about all of them, but if you wanted to schedule public transport, then the decisions, yeah, okay, really frustrating. The decisions that you make would be something like the time that everything arrives to its station, the capacity of each train that you assign to each track, or something like this. And then you have some constraints like, okay, you can't have two trains in the same place at the same time, and you have to have a minimum amount of capacity, and you can't schedule negative number of trains at each station, and this kind of stuff, okay? And the thing that you want to optimize is ideally happiness of the passengers, okay, more likely cheapness of the system. And okay, and whether or not this problem is easy to solve depends a lot on the types of variables that you include and the type of model that you have. And you hope that the problem will be somehow easy. So One that you'll have seen probably is this fitting a model to measured data. So yeah, this would be something like solving a least squares problem. Okay, so I give you a bunch of inputs and outputs, and you want to find a linear relationship between the two. So you solve some optimization problem where you're minimizing the square of some errors. Okay, and this one is one of the few cases where we can just write down what the answer is. Most of the time, this is not possible. A much more difficult one is this one here at the bottom, this shaping aerodynamic components. This one is extremely nonlinear. There's all kinds of weird functions. It's extremely difficult to really even say what you're trying to do. And there you absolutely have to have some kind of numerical method to do it. So you have a whole range of degrees of difficulty and different types of problems here. And the one that we're really interested in, and the one that we should keep in mind, are these last two, the linear controller design and the trajectory design for dynamic systems. So for linear controller design, you would want to know something like, if I give you a control problem and I want to minimize the discounted quadratic cost of the state and input, and I want to design a controller that's stabilizing and minimizes this cost, then my decisions would be the parameters of the controller that I want to pick, and my objective would be whatever cost function you gave me, and my constraint would be to make the controller stabilizing. Okay, and then the thing that we're really interested in for predictive control is this trajectory design. So there we say, I give you the dynamics of the system, and you want to choose some inputs for the system that make it do something nice. So specifically, you want to make it be stabilizing if you run it in receding horizon. But before you even get to that, you have to choose the inputs such that you stay inside the constraints and minimize some cost. So we can write down an optimization problem which says, choose the actions of the system such that we steer it inside of the constraints all the time. Okay, now, I didn't say how to do that. That will be the topic of the lectures after tomorrow. But I think in the exercises this afternoon or maybe tomorrow afternoon, you'll start to see how you can do this last bit. Okay. So, right, so now this is all kind of so far quite vague. So now I want to write down, I want to get rid of the little, yeah. Okay. I really want to get rid of the little arrow. I'll move it over there. The thing about Apple products is they just work, right? They always work. Okay. Right, okay, so when I describe an optimization problem, I can write down everything from the previous slide in the same way if I think about it in sufficiently generic or abstract terms. Okay, so if I say that I have an optimization problem, I say I have some parameter x that I want to choose. Okay, I haven't even said what type of thing x is. X might be a function, x might be a scalar, it might be a vector in Rn, might be a matrix, might be anything for the moment. I have some function of this decision, okay, which I call my objective function. I say that x has to live inside a set uppercase x, and then I say here that uppercase x is a subset of this script x, okay? So what's the difference between these two things? The script x tells me usually the type of decision that x is. So x might be a vector in Rn, so then this script x would just be Rn. X might be a function, and then script x would be, I don't know, the space of all continuous functions. But then within that space, I have some restrictions. So if I have a vector in Rn that I want to pick, but I want it to consist only of non-negative values, then I would say that script x is the set of all non-negative numbers. Okay, so there's a distinction between the space that I live in and the region of that space that I'm allowed to optimize over. Okay, but in any case, I take all of my decisions. I might have more than one. I collect them up in this vector x. I call them all my decision variables. That's this bit. I tell you what is the domain of these variables. That's the set script x. And then I tell you where in that domain you're allowed to, or from where in that domain are you allowed to select your decision. We call this the constraint set. And then you tell me over that constraint set which one is the best one. Okay? And most of the time, you cannot just write down the answer to a problem like this. It's extremely rare that you should be able to just look at the problem and immediately write down the solution as you would with least squares. So instead, what you have to do is you have to solve the problem in some numerical way. And the method that you use depends on the type of problem. Okay, and we can, if we want, summarize all of the above by writing it in this form, where I take the function, I say I want to minimize it, and then underneath the min, I say something about the rules that I have to follow when I make my decision. And so it's equally valid to write it this way or this way. It doesn't make any difference, but you see it both ways. And much of the time you'll see some kind of mix where you have here min over x, and underneath here it will say x in the domain, and then down here it will just tell you what are the constraints. Okay, but don't become confused if you see things moving around a little bit, because, okay, it's entirely down to personal preference. Okay, so we have some problem like this, and we say that this is a mathematical optimization problem. It's very likely to be nonlinear, so we say it's a nonlinear mathematical program, or just an NLP. And, okay, if we have an NLP, usually we're unhappy because we don't know what to do. So what we want to do is we want to describe some variations of this problem that we think we have some reasonable chance of solving. And I think it's fair to say that unless you're really lucky, if your problem is not convex, then you've landed in the really difficult problems to solve category. And if your problem is convex, then you've probably landed in the easy to solve category. Not necessarily, but probably. So what we want to do most of the time is, what we would like is for our problem to turn out to be a convex one. And so that's the thing that we'll focus on for most of today. Okay, so now, if I'm thinking about specifically problems where I'm optimizing over vectors in Rn, then it's a little bit easier to be maybe more clear about what my constraints are. So instead of writing it as I did on the previous slide, I write it this way. So now what I do is I take my decisions and I call them x. And it says here, right here, that the domain of my decisions is script x, which is Rn. So I have a number of decisions. I don't know, if I'm wanting to design a trajectory, maybe my decisions are the input at each time. So I have a collection of inputs. So it lives in Rn and is, okay, just some integer. And this is the thing I want to choose, and script x just tells me what type of variable it is. I have some objective function, which I call f0. And then instead of having the uppercase x, which tells me what my constraints are, I explicitly write down some equations and some inequalities that tell you what this set is. So if I can, right. Okay. I really want to figure out how to write on here.
Right, there's a menu.
It's disappeared, though. There was a menu there.
You have to bring down the cursor.
To bring down the cursor? What do you mean?
Bring down the cursor to the bottom.
Ah, okay. All right. Yeah. You know, the sad thing is I even tried this yesterday, and I had it all figured out. It's not really worked out for me. No. Yeah. Okay, well, whatever. You think I have to? All right, thankfully it's all being recorded, so you can all see my flailing later at your leisure. Okay, so, right, so what I have, yeah, come on. All right, so, sorry, go back here. So if I could write on the screen, which for some reason I cannot, then I would try to write on here that these constraints, or the set of x's that satisfy these conditions, these collectively add up to this set uppercase x. Okay, so the set uppercase x is the set of all decisions that satisfy all of these constraints at the same time. So you can imagine that the equalities, they define something like a surface in Rn, and I have to be on every single surface. And the inequalities define surfaces, and I have to be on one side of each of those surfaces. And so I get the intersection of all of these things, and I have to live somehow in that region. So, okay, this is not mysterious. So if I had a control problem where I had to choose inputs which are non-negative, say, so I want to choose the amount of something that I produce, then this inequality would actually just be x1 greater than 0, x2 greater than 0, and so on. And if I say that they all have to add up to 0 at the end, or they have to add up to some budget at the end, then I would have an equality constraint. Okay, but I just write it down in these terms because it's relatively generic. Okay, so I have both equalities and inequalities. I can have different amounts of each. I can have m inequalities and p equalities. I can have none of them if I want, okay, in which case the problem would have no constraints. And if I want to solve a maximization problem, then all I have to do is minimize the negative of f0. Okay? So I solve this problem where I minimize the negative of f0, I get an answer, and then I should be careful to remember to change the sign of the value at the end that I got. Okay. Now suddenly the thing has appeared. Okay, well, fine. Can I write? Now I can write. Okay, minor victory. That's good. Okay, so just so that, because I don't want it to be kind of mysterious, so just so that it's absolutely clear what I'm saying, I realize this is a really easy example, but if I have a box, okay, suddenly and possibly momentarily I can write with my pen, so I'm going to do that. I have this box here. There's absolutely no need for me to have written on there. I just wanted to test it. Okay. Okay, so I have this box, and I want to check, or I want to choose the point inside the box that's as close as possible to this point 3, 2. Okay, so my decision variable here is a point inside the box, so it's a vector in R2. And I have some constraint which says that I have to stay inside the box. And I have an objective function which is the distance of the point that I choose to this point 3, 2. And well, when I say the distance, I mean the Euclidean distance. Okay, I could mean the distance in some other sense, but here I mean the 2-norm distance or the Euclidean distance. Okay, so now what I want to do is I want to take my problem and I just want to write it down in this standard format that I have. So, okay, so I write here min, because it's a minimization problem. I tell you what is the space of variables that I'm optimizing over. I write down my objective function here, which is just the squared distance to the point that I pick. So the point I pick will be called x1, x2. And then I have some constraints which say I have to live inside the box. Okay, so these constraints I could also write as -1 less than or equal to xi less than 1. Okay, for each I. This says I just have to live in the interval. And I've just written them down by taking the left-hand side and rewriting it here. Or if I want, I could write it this way, that the infinity norm of this vector should be less than 1. Okay? It doesn't matter which way I write it. But I prefer to write it in nice linear inequality terms like this. Okay, for reasons which will become clear later. Okay, now, maybe you could just look at this problem and solve it, okay? You might guess, well, it's right here. Okay, maybe you won't. Does it? Yeah. It's right here. That's the minimizer. And I can tell just by looking. But what I can't do is I can't, for a generic problem of this type, write down the solution in any analytical way. Okay, so I have to do it in software. I need some algorithm to do it. And, well, okay, people spend a long time working on algorithms, but for today and tomorrow, we actually won't talk about how to solve the problem, because in a sense, this doesn't really matter. And the reason is that plenty of people have already spent a long time figuring out how to solve problems like this. And most of the difficulty when you solve optimal control problems or optimization problems of any kind is not solving the problem once you have it. The difficulty is getting the problem in the first place. Okay, so I give you some extremely elaborate variation of a problem description like that, and then you have to bash it so it looks like a nice problem like this. And it's entirely non-obvious how to do that sometimes. Okay, but if you can get it into a standard format, and in particular, you can get it into one where everything is nice and convex and you have nice continuous functions and so on, then usually you're in really good shape, unless you want to solve it really fast or unless your problem has some really strange structure or is really huge or something like this. So most of the trick now is posing your problem in the right way. Okay, unfortunately for us, when we do predictive control, we're one of the groups that cares about making it go really fast. Okay, so then we have to think, how does one go about solving this? But most of the time, the modeling is the problem. Okay, so now we should just talk about sort of terminology. I apologize in advance for the boring nature of the terminology slides. Okay, but just we have to make sure everyone's using all the same words. So whenever we have an optimization problem, if I don't tell you anything about it, then we just say that it's nonlinear. Okay, and we say that it's nonlinear because nonlinear doesn't tell you what it is; it just tells you what it's not. Okay, so I'm not promising you anything when I say it's nonlinear. So we say we have a nonlinear optimization problem. Okay, here. I hope that wasn't a mistake. So we have an optimization problem, and we want to talk about what are the generic features of this problem. So suppose that I can solve it, and I can make this value arbitrarily negative. Okay, so then I would say that J star, which is the value of this problem, is minus infinity, and so I say that the problem is unbounded below. So there isn't any solution to the problem because I can always choose some x that makes it even more negative than any x you might pick. Okay, so this is kind of somehow a defective problem if I have an unbounded problem. If this constraint here is empty, so maybe I should write actually uppercase X if I want my notation to be consistent. If this set is empty, then there aren't any choices that will satisfy this condition. And so in that case, we need to assign a value to the problem, and we just say that it's infinite. Okay, the problem is extremely bad, or we can't do it. So when you solve a problem and you get an infinite value, that means it was usually unsolvable. Okay, and if I take, instead of this guy being empty, if I take it to be Rn, if I'm thinking about optimizing over vectors, then we say that the problem is unconstrained. And if it's unconstrained, maybe it has a minimum value or maybe not. Okay, and then something that sometimes troubles people is that if I'm able to solve the problem, and if J star is a finite value, then I have to think about what's the right answer? What's the x that achieves that value? So there might be one solution. If J star is finite, there might not be any x that makes f equal to J star, even if it's finite. Or there might be exactly one, or there might be a finite number, or there might be an infinite number. Basically anything can happen. Okay, so now I try to show you. Okay, now I may really regret trying to do this, but okay. So I'm just going to try to draw a picture for you of a case where you get multiple optimizers and then a case where you get an infinite number of optimizers. Okay, so I might have a function like, I might have a function like fx is equal to 1 minus 2x. Yeah, okay. One minus 2x squared plus 4. Plus x to the fourth. Okay. My handwriting is not usually this childlike. Okay, and so I can just draw this function. And it looks something like this. Okay, so I have two minimizers. They're here and here. So the minimum value of this function is 1. So J star would be 1. But then argmin would be plus or minus 1. Okay, so I have two distinct notions of what the solution is. I have the value and then the input that achieves the value. Okay, so that's a case where I have a finite number of optimizers. Another one would be something like this. So I might have a function that looks like that. And now I have, okay, assuming that I'd drawn the bottom one level, now I would have an infinite number of minimizers, because anything between here and here achieves the same value, but the minimum value is still 0. Okay. And I'll show you in a little bit a case where I have a minimum value but no minimizer, but we'll come back to that. Okay. Right, so this is just kind of a warning here that you have to be a little bit careful if you want to make sure that you actually get a solution, and you want to be sure that this solution is unique. And this point is really important for control, because if I solve an optimization problem in a control system, and I want to choose as my input to the system the optimizer of this problem, then I would really like the solution to be unique. Otherwise, I solve the problem twice in a row, and I get a totally different answer. And if I'm putting then these different answers into my system as commands to my actuator, then I'm going to get all kinds of funny behavior like chatter or other weirdness. So I don't want usually to have, at least in control, multiple minimizers. I want there to be a clear, correct answer. Okay, so we'll talk about how we know when we're going to get a unique answer or not. Okay, so now a little bit more terminology. If I have a vector x, and it satisfies all of the constraints, then we say that x is a feasible point. Okay? And I will always satisfy, in order for it to be feasible, by definition, it has to satisfy the equality constraints with equality. But if I look at the inequalities, one of two things can happen. I can either satisfy it by having it equal to 0, or I can satisfy it by having it strictly less than 0. And if I take a point x and it satisfies all of the inequality conditions with a strict inequality, then I say that the point is strictly feasible. Okay, and there's a diagram in a few slides that shows you the difference between these two things. Okay, now I can talk about the optimal value. Okay, that's the lowest value that I can achieve. And I may or may not have multiple solutions which, at least in their local region, is optimal. So I say that a point is locally optimal if I take that point and then I don't allow myself to deviate it by more than a ball of a certain radius r. So I say I take my point, I look at all of its neighbors in some sense, and if that point x is the solution to this problem, which is to minimize over the neighbors of x, then I say that x is locally optimal. Okay, and if it's true with r infinite, then I say it's globally optimal. Okay. Okay, now that's the value, but now I can talk about the solution. So I say that the solution is actually an optimal solution if it's the one that achieves the lowest value. And I say that it's a local, it should say local optimizer maybe, if it's the best one in its neighborhood. Okay, now I said at the beginning that most of the time we write min something, and when we do that, we're sort of committing a kind of mathematical foul. Okay, and the reason is that in this problem, it might be the case that the problem has a finite value, but there isn't actually any vector that actually achieves this value. And so I try to draw you a picture of a case where this happens. Oh no, I lost my little thing. Oh, that's so frustrating. Okay, it doesn't matter. Okay, so okay, I'm sorry. Okay, so what could go wrong? So I said that you can have a problem that's infeasible, in which case it has an infinite value, or it could be unbounded, in which case it has an infinitely negative value, or there might not be any x that does it. So here's just 3 examples of when this happens. So here I say that I want to minimize x squared, and I want x to be both I want x to be both less than -1 and greater than 1. Okay, so it has to be everywhere to the left of some negative number and to the right of some positive number. And, well, okay, there aren't any x's that do that, and so I say that the problem is infeasible. And it makes absolutely no difference what objective function I put here. Okay, it only matters that this set is empty. So whatever function I put here, the value of this problem is infinite. Okay, because I can't solve it. Okay, on the other hand, I might have a problem which is, so this problem is in a sense too hard. Okay, I can't find any x that does it. The other extreme is I have a problem which is somehow too easy. So I have a function which can be made arbitrarily negative within its constraints. So here I say, okay, x has to be less than 0, minimize x. Well, you can make it as negative as you want. And so I say this problem is unbounded below and its value is minus infinity, and so it doesn't have an optimizer, unless you want to think about x being minus infinity as an optimizer. But now it matters what objective function I picked. If I'd picked x squared here, then this problem would have a clear solution, which would be 0. Okay, and then I have one final case, which is that I might have a problem which has a clear minimum value, but there's no vector x that achieves the value. So if I could write on the screen, which for some reason I cannot. This is so annoying. Okay, then I could imagine that this function e to the minus x is a function that's, and it has to be bigger than 0. It's a function that's decaying towards 0 as I increase x, but it never quite gets there. Okay? But if I claim to you that the minimum value of this problem is any number greater than 0, then you can quite easily find for me an x that produces a value lower than that. Okay, so if you claim that the optimal value of this function is some epsilon, then you can figure out an x that achieves that epsilon. It's log of 1 over epsilon. Okay, and then you make x a little bit bigger than that, and the value is even lower. So this function decays towards 0, but it never quite gets there. And I have to make x bigger and bigger to get the function to be smaller and smaller. So here I would say that j star is 0, because j star is the greatest number that's lower than everything I can choose here. Okay, it's the greatest lower bound. But there isn't any x that solves this problem. And so again, I have now kind of half a solution. I have a value, but I don't have any optimizer. And so we might, depending on our purposes, conclude that this problem is defective in some way, or maybe we're happy just to know what's the minimum value. It depends on whether we really want to know what is x, or do we really want to know what's the value. Okay, so those are the things that could go wrong. And then one other thing that might happen is I might have some constraints in my problem, but I may not actually need all of them. So we say that a constraint is, for a given point x bar, we say that one of these constraints is active if the function is actually equal to 0 at that point. Okay, so that means that for that particular x bar, that constraint matters. Okay, and so the equality constraints always matter. Okay, so I'm always restricted to satisfy the equality constraints. But the inequalities may or may not actually be tight for a given point x. And when the function is not tight for that point x, then we say that the constraint is inactive at that point. Okay, so the inequalities are sometimes active, sometimes not, and the equalities are always active. And if the inequality is never active, or in other words, if the inequality never makes a difference about which x's you're allowed to choose, then we would say that the constraint is redundant. Okay, it doesn't change the feasible set. If I take it away, I have essentially the same problem as before. So, okay, completely trivial example. Minimize some function, x has to be less than 1. Also, x has to be less than 2. Okay, the second one's not doing anything for me, so I can throw it away if I want. Okay, now, identifying which are the redundant ones is not always so easy as this. Okay, but in principle, I could find them and throw them away if I needed to. Okay, so now we have a picture. So you can imagine here that I have a function in R2, and these contour lines here are showing me curves of equivalent values. So I have the actual minimum value of my function is right in the middle right here. And then as I move away, I'm moving up in value. And so I would like to choose this point, but I can't because it's not inside my constraints. So I have here this white region. This is the feasible set. And you can imagine it being defined by 4 inequalities. So each one of these curves here would be one of the functions fi. And fi less than 0 is everything on this side of the curve. And I have another function here, which might be f2. And it allows everything on this side of the curve. Okay, and likewise with the other two. And because I have to satisfy all of them at the same time, I have to live in the middle or in the intersection of these sets. Okay, and so you can see here I have a funny curvy-shaped set. So if I take this point, it's the lowest value point inside this feasible set, at least in its local area. So I say that this is locally optimal. Okay, so that point is the local optimizer, and the value of that point, or the curve that I'm on, is the locally optimal value. And then I have another point over here, which is the global optimizer. I can't do any better than that. I call it x star. And it has a value, and it has an x that achieves the value. Okay, so I'm somehow happy. And everything on the boundary of this set, I would say, is a feasible point. And everything on the interior of the set, I would say, is a strictly feasible point. And if I take a point somewhere over here, then I would say that this line here is an active constraint, and all of the others are inactive. And I take something in the corner, then 2 of the constraints are active, and the other 2 are inactive. Okay, so this is just a kind of cartoon of the type of problem or the sort of geometry of the problems that I want to solve. And you can see here that this region, because of the shape of this region, I end up with 2 local minimizers. Okay, and the reason is that in this case anyway, one of the faces of this shape is pointing or bulging in. Okay, and that's because this is a non-convex set. So I have here a nice function. Okay, it's continuous, it's convex, everything's nice about it, but it's got one region of the feasible set that's kind of sticking out, and then one over here that's sticking out. And, well, this is not so nice. So what I want to do is I want to think about problems where this doesn't happen, and instead everything is nice and round, and the functions are nice and smooth and convex. And then this kind of thing won't happen. Okay, but we'll come to that later. Let me see what. Okay, so now I said earlier that we have this standard problem form where we say minimize over x in x, some set, and then also, by the way, we have all of these other inequalities. And it's really up to me what I want to call the set uppercase x and which constraints I want to stick into these inequalities. And it doesn't really matter which way around I do it. So I can give each one of these 2 choices a name. So if I restrict x to be a point that satisfies this inequality or that equality, then I say it's satisfying these explicit constraints. Okay, but if I take as the domain of my function, or the set uppercase x, if I take that to be something other than Rn, then this is, in a sense, also a constraint. Okay, so if I said that the domain of my function is all of the non-negative numbers, then the vector being non-negative is a constraint. Okay, but I've just chosen not to describe it this way. I've chosen to describe it in some other way. So this would be an implicit constraint. But my x, it always has to live in the domain of the function f, and it has to live in the intersection of the equality constraints and the inequality constraints, or the domains of these things. Okay, and if I have no inequality constraints and no equality constraints, then I would say that it's unconstrained. Okay, but it might not really be unconstrained because I might have this implicit constraint in the domain of f. So, okay, this is kind of a technical point, but it's just, I say it so that you are aware to be careful that you should sometimes think about what's the domain of the function when you ask whether the problem is unconstrained or not. And sometimes it helps to choose for the constraints to either be explicit or to stick the constraints into the domain of the function. Sometimes this is a kind of convenience. In the end, it doesn't make any difference to the solution, but sometimes it's easier to write it one way or the other. Okay, so here we have an example. This is an unconstrained problem because I'm just minimizing a function. Okay, but it has an implicit constraint, which is that the domain of this function is not the whole space. Okay, so I have to have all of these numbers being positive in order for this function to make any sense. Okay, so I have really a domain here, which is defined by this set, which is just implied by the choice of the domain, or implied by the choice of the function that I picked. Okay, but for the most part, we could even, if we wanted to, write this down explicitly as an inequality constraint, and then we wouldn't have to worry about the domain of f anymore. Okay. Right, so maybe we do one more slide and then stop for 5 minutes, 10 minutes? Happy? Unhappy? Yes? No? Yeah? Okay. Okay, so now sometimes what I have is I have a number of constraints, and I just want to know, are these constraints consistent with each other, or do I have a set that's empty or not empty? And I can pose this as an optimization problem if I want to. So what I do is I take my constraints, I write them down as a bunch of equalities and inequalities, and I want to know, is there any x that satisfies all of these conditions? Okay? Now this isn't really an optimization problem because I'm not minimizing anything. Okay, and I need something to minimize. Well, okay, I can pick anything I want, so I pick 0. Okay, minimize 0 subject to these constraints being satisfied. And suppose I have some solver that will work for the type of constraints that I picked. I solve this minimization problem, and I hope that it gives me some x back, and I hope it reports to me some value. And if it reports to me the value 0, then that says it was able to solve this problem, and it says that the x I have is consistent with these constraints. And if it reports to me the value j star is infinite, then that means it couldn't find any point that's consistent with these constraints. Okay, so this is a kind of extremely simple variant of an optimization problem. Okay, and it's just a way of checking whether a set is consistent or not. Okay, so now we stop for 5 minutes, maybe till 10 past, and then come back. Good. Okay, for some finite amount of time, I'll be able to use the pen again. Okay, so now what I want to do is just sort of mention to you some common types of optimization problems and point out some that are easy and some that are hard. And in particular, common ones that you will see when you come to the control part of the course, so the MPC part of the course. Okay, so what we can do is we can divide optimization problems roughly into easy ones. And by easy, I mean convex. It's not to say that all convex problems are easy or that all non-convex ones are hard, but generally convex problems are easy and non-convex ones are hard. And the two most common types of easy problems or convex problems are linear programs and quadratic programs. So if I take a problem where I have a linear objective function, okay, so just some linear combination of the decisions that I want to make, and I define my equality constraints and my inequality constraints entirely in terms of linear functions, then I would get a problem that looks like this if I think about the figure that I showed you before. So when I say gx is less than h, think of g as being a matrix, h as being a vector, and so even though I've written only one inequality here, it's actually a collection of inequalities because every row of g times x has to be less than every element of b. Okay, and then likewise with the equalities. So if I think about what this set looks like, then we'll see it more later. Every single row of this inequality will define a plane, and the choices that I'm allowed are everything on one side of the plane. And if I take the intersection of all of these sides of planes, then I get what's called a polytope or a polyhedral set. And so here I'm trying to minimize a linear function. So here the dashed lines are the level curves of this function. And I'm just trying to push down in this direction this function until I'm just at the boundary of the set. Okay, and we call this a linear program because all of its components are linear. And then a variant of this problem, which is the one that we will solve most of the time for predictive control, is what's called a quadratic program. And here all I do is I just add one quadratic term to the cost function. And I have to be careful because it matters what properties this matrix P has. So if P is a matrix which is positive semi-definite, so this notation means that all of the eigenvalues of P are non-negative and P is symmetric, then this problem is nice, okay? And the reason is that the function is a convex one or a bowl-shaped one. So if I wanted to minimize, for example, the 2 norm of x squared, then I would just choose P equal to I, and all the eigenvalues are 1. Okay, and this would be a nice problem to solve. If this condition is not satisfied, then it's not so nice anymore. And so I have to be careful to check when solving a quadratic program whether this condition is true or not. Okay, and in general, both of these problems are nice in the sense that there's lots of solvers for solving them. I can solve the problem in a polynomial amount of time, where the polynomial is some polynomial function of the data in my problem, and I can be assured that I'm going to get the optimal solution, and I can easily write down conditions under which an optimizer will exist, and so on. And more importantly, there's lots of nice software where I can just plug in all my data and throw it into MATLAB, and it tells me the right answer. And I can solve a problem that looks like this, maybe for even many millions of variables. And likewise with this one. Oops. Likewise with this one here. Okay, now that's not to say that all convex problems are easy. Some of them are also horrible, and they're not always polynomial time and all this. But these two, which are the two standard ones that we'll see, they are nice, and they can be solved in polynomial time. And so this is the form that we would like our control problems to take when we solve them. Okay, and so these are the easy ones, and then harder variations of these would be one where you take the same quadratic program as before, but you just make P not positive definite. Okay, so now instead of the function being bowl-shaped, it's maybe domed, okay, so it's concave, or maybe it's got a saddle point, so it goes down in one direction and up in the other direction. And then it's not so easy, okay, and you can kind of see from this figure why this is the case, because maybe this is the saddle point of the function, and it's going down in this direction, okay, but it's also going down in this direction. So this might be the optimal point, or this point way over here might be the optimal point. Okay, and it's not so nice. And then I can also add other funny-looking constraints onto my variables. So I could take my linear program, which is nice, and I can say, by the way, the x's have to be either 0 or 1. Or maybe some subset of the x's have to be 0 or 1. And so now I have to choose an x that lives inside this region, okay, which is not so bad. But also it has to be one of these points that lives inside the region, if it's some kind of integrality constraint. And this is also, okay, not so nice, let's say. You can still solve this. There's lots of research into how to solve these problems. There are solvers that will do it for you. But, I mean, I think, broadly speaking, having a problem with this constraint is a lot worse than having one without it, okay? Okay, so we're going to talk quite a lot about what, or how to characterize a convex problem. And you'll see tomorrow why these problems are, in some sense, easier to solve. Okay, so now I said that the real difficulty when you do optimization most of the time is actually writing down your problem. It's not solving it, because plenty of people have spent a long time figuring out how to solve problems in various forms. So most of what your time gets spent on is trying to write down your problem in some standard-looking form. And then once you've done that, then you can plug it into MATLAB or some other optimization software and solve the problem. So I just want to show you roughly how to do this and give you a pointer to two different software tools that are available to you. So suppose I have this problem, minimize the sum of the absolute value of these two functions, subject to x1 and x2 living inside some linear constraints. So here I actually have 4 constraints, okay, and I have a relatively simple function. Okay, now this is this function here is not a linear function, okay, because it's got an absolute value in it. But it turns out that you can rewrite this problem as a linear program. by adding a few variables, and I'll show you how to do that in a little bit. Okay, so for the moment, let's just say that I have my problem in this form, and I want to solve it. I shouldn't try to solve it by hand. Okay, maybe 2 variables you can solve by hand. More than 3, and probably not. Or at least it's not worth the effort. Let's say that. So you could write it as a linear program, and then you could stick it into one of a great variety of software toolboxes. So when I wrote this slide, I thought I need to think of all the optimization software that I can think of that would solve this problem. And so these were the first 10 that I could think of. Okay? And there's lots more. So, and some of them are free and some of them are not. So Cplex and Gurobi are commercial. If you have a university email address, then you can get a free license. GLPK is free. Express is commercial. Okay, this one's free. That one's free. Forces is one that comes from ETH. These 2 will solve semi-definite programs, not just linear programs. Okay, IPOpt will solve nonlinear problems and so on. So every single one of these can solve the problem here, and some of them can solve greater, sort of broader classes of problems. But the point is that all of this, or most of these, are free and you can use them. And the difficulty is that they all have totally different interfaces. Okay, so you write in MATLAB, you define this problem, and then you want to solve it. Okay, so you try Cplex, and okay, Cplex will certainly solve this problem for you, but the license is not available or whatever, so then you want to use the next one on the list, but the arguments to the function are totally different. Okay, and this is a pain. So what's happened in the last maybe 10 years or so is that people have spent time trying to define slightly higher level modeling languages so that you can just write down this problem in some standard looking nice form, and then you can solve it, and you can solve it with any one of these solvers just by selecting some flag or argument somewhere in your code. Okay, so this makes your life a lot easier. Okay, so just so that you know that this is available, because the worst thing you could do is, I mean, truly the worst thing you could do is try to write this problem for things. Model your problem using that tool, and then just give it to any one of these solvers. So now I just wrote on the next 2 slides example code to show you what this looks like. So YALMIP is YALMIP is not a solver. Okay, instead think of it as a modeling toolbox. Okay, it's in MATLAB. You can download it for free. It was developed by a guy named Johan Lofberg when he was here at ETH. He's now in Sweden. He's still working on it. And what you can do in MATLAB is you define, first of all, your variables. So SDP var is the name in YALMIP for decision variables of problems. You define your function, which is whatever your objective function is. You define your constraints by saying that big X is the set of all X's that satisfy these inequalities, plus or intersected with the set of all X's that satisfy those inequalities, and then you say solve. Okay, and it solves it for you. And it will solve it for you with whatever its default solver is. And if you don't like the answer, then you can tell it to use a different solver. Okay? And you hope that they give you the same answer. In this case, they would, because the problem is nice. Okay, so this is, as I said, this is free. It's relatively user-friendly. It's the one that I usually like to use. But there's another one which is a little bit newer. From Stanford, okay, equally good, maybe even better, I don't know. I use the other one just because I'm used to the other one, called CVX. And it's broadly the same idea. So you define your variables. First of all, you say, I'm about to solve in MATLAB, I'm about to solve an optimization problem, so begin the definition of my problem. And then you say, okay, these are my variables. And then I just actually write down my problem in a form that looks very much like this. Okay, so if you like to make your code look as much as possible like your optimization problem as you would write it on paper, then maybe CVX is the one to use. And then you say CVX end, and it solves the problem for you. Okay, and again, it solves the problem for you with whatever its default solver is. And if you don't like it, or you don't like that solver, or it doesn't work for some reason, then, well, you just tell it to use a different solver. Use, I think it's CVX_solver, and then the name of the solver you want. So CVX solver, Mosaic, or Garobi, or whatever you like. Okay, and so the point is that you should do this and not worry about how the problem actually gets solved until you have a real reason to worry about it. Okay, and in predictive control, that's when you want to solve it really fast, or you want to solve it on an embedded system or something. But okay, if you're doing things in MATLAB, then I would strongly suggest to you start here. Okay. And I think some of the exercises that you'll do this afternoon and tomorrow will invite you to do it that way. Okay, so now we're going to talk about convexity and convex problems. And so a convex optimization problem is just one where all of the constraints are convex and all of the functions are convex. So if you know what these two things mean, then I guess this will be very easy for you. But okay, we just now briefly discussed what is a convex set and what's a convex function. And then if all of your functions and sets are convex, then you have a convex problem. Okay, so a convex set. So you can think about a convex set. I mean, it has a clear definition, which is written here. But basically, a convex set is one where I've cleverly discovered how to, yeah, okay. So a convex set is one where if you pick any 2 points, 1 point there and 1 point here, then the straight line between those 2 points stays inside the set. Okay, so you pick any 2 points you like inside the set, and you connect them up. And if that connection doesn't go outside the set for any 2 points that you pick, then you say that the set is convex. And we can write that in slightly clearer terms. Okay. Up here by saying that a set is convex if and only if for every x and y that you pick, so you pick 2 points, you call them x and y, any convex combination buys an x. So a convex combination is you take your 2 points, you pick a number between 0 and 1, and you call it lambda, and you multiply the first point by lambda, and you multiply the other point by 1 minus lambda. So if I take my, my drawing again, lambda tells me the fraction of the distance that I've moved from one point to the other. Okay, and every point along that line, so this line is parameterized by lambda moving from 0 to 1. Every point on that line has to stay inside x. Okay, that's what this says. Yeah. That's what this guy here says. Okay, so I pick the 2 endpoints and I have to stay inside the set. And if I look at this one, okay, this is clearly true for a ball. I pick any 2 points in the ball, I go between them, I stay inside the ball. Likewise for any polyhedral set, and likewise for the intersection of the set that's on either side of these two lines. So here the set is actually unbounded. You can think of it extending infinitely far in these two directions. So it's like an infinitely long pipe. But no matter which 2 points I pick, I stay inside. And then I have funny examples like this one down here. Okay, if I pick this endpoint and that endpoint and I draw a line between them, I'm going to end up outside the curve. Okay, or if I pick this one, most of the combinations of points I might pick would have their interpolation staying inside the set. But if I pick 2 points either side of the hole, then, okay, I go outside the set. And then I can even have this funny situation where I have a set. The blue part is the boundary of the set. And maybe I make the set open in one little segment or one piece of its boundary and everywhere else closed. And so if I take a point right there and then I take the other point right there and I go between them, then I find myself outside the set. Okay, so this one would be non-convex. And generally you can think of a convex set as being one which is sort of got nice rounded sides and doesn't have any holes in it. Okay, and the reason why this is nice is because when I want to solve an optimization problem, if I take any point and I evaluate my objective function at that point, and then I want to improve upon the value, so what I want to do is I want to go downhill. Okay, and what I find is that I can always move in straight lines around this function or around this set without going outside. Okay, if I have holes in it and I find myself over here and the best solution is on the other side of the hole, then I can't just go in a straight line. I have to somehow go around. And this makes it harder to solve. Okay, so this is, okay, I assume that you've seen all of this before. So this is a definition of a convex set. And now we can write down, or we can describe a whole bunch of sort of basic or generic convex sets that we might work with. Okay, and this is going to tell us the types of constraints that we can impose on our problems. Okay, so first of all, an affine set is a convex set which is just the solutions to AX equals B. So here I have a line or a plane. This is a solution to some equation AX equals B. Every point on the line is in the set. And if I take the special case that B is equal to 0, then I get this line passing through 0. Okay, so now I have here the set of x's that satisfy AX equals 0. So this is the set that's the null space of A. Okay, and so this is a convex set, and I can, okay, I claim to you that it's a convex set, and you can prove it very easily. You just plug in the definition of convexity, and you just check whether every point satisfies it. So we suppose that x and y are 2 points in one of these planes or one of these affine sets. Okay, so I know that both x and y satisfy AX equals B or AY equals B. And then I just pick any point that's on the line between them. Okay, so I take lambda x plus 1 minus lambda y. That's a point in between. I multiply them both by a to check whether this intermediate point satisfies my equality constraint. Okay, so because the function is linear, I end up with lambda ax, 1 minus lambda ay. But I know that ax is on the plane, so it's equal to b. And I know that ay is on the plane, so that's equal to b. And I add it all up and I get b again. Okay, so this is this point on the line between them also satisfies a times that intermediate point equals b. Okay, so therefore the set is convex because I didn't say which 2 points in the set I picked. I just said pick any 2 points. Okay. So now, okay, and this is an example of a set that's defined by inequality. Sorry, an equality. Okay. So now we can think about a point that's defined, or a set that's defined by an inequality. So if I take an affine set, which I had written as AX equals B, and I take the uppercase A to just have one row, and I call that row A. So now I just have one constraint, okay, one equality, and now B is a scalar. Then this set is a special type of affine set called a hyperplane, okay? And the vector A is the normal vector to the plane. So here I just write down again AX equals B, okay? And then I have this vector little a, which points straight out of it. This is the normal to the plane. And if I take here an equality, then I just get the line. Okay? But if I relax this thing to an inequality, what I get is everything on one side of the line. Okay? So I take all the x's that satisfy ax less than b, and I get the line plus everything to one side. And this is a general feature of inequality constraints, that if you take the inequality constraint and you make it an equality, you get some curve. Then you make it an inequality again, and you get everything on one side of the curve. Okay, and I can talk about this set being either open or closed, depending on whether or not I make this strict or non-strict. So an open set would be this gray region, but not including the blue line. And a closed set would be the gray region, but including the blue line. Okay, and because the blue line is when it's actually equal. Okay, and the point is that hyperplanes and half spaces are always convex sets. Okay, and the difference between a hyperplane and an affine set from the previous slide is that a hyperplane in 2 dimensions defines a line, in 3 dimensions it defines a plane, so it defines always a surface of dimension 1 lower than the space that you're in. But an affine set could be a plane, it could be a line, it could be a point, whatever. Okay, so that's a nice example of a convex set. That's the one that's probably the most commonly used when you model your optimization problems, but there are lots more. So we talk now about some of the others. So we can talk about a cone. So a cone, or the definition of a cone is a set where if you take any point x inside the set, and then you scale it by some non-negative number, then you stay inside the set. So what this means is that if I take any point here, and I just move in a straight line away from 0, then, okay, that's not a very straight line, but if I move in a straight line away from 0, then I stay inside the set. And if I include the point 0 down here, then I say that the cone is pointed, because if I look at the figure, then it looks pointy at the end. Okay? But if it doesn't include the point 0, then we say that it's not pointed. And it's not the case that a cone should always be convex. So here's over here we have another example. So I take this point right there. If I scale it by a non-negative number, I just get everything moving in that direction. Okay, so this set is clearly a cone. But it's not a convex cone. And the reason is that if I pick this point, and then that point, and I draw a straight line between them, then I find myself outside of the set. Okay, and we say that a conic combination, instead of a convex combination, is any point where I take 2 points inside the set, and then I multiply them both by some theta, and the 2 thetas have to be non-negative. And the only difference between this and a convex combination is that in a convex combination, I have to have the 2 numbers summing to 1, and here I just have to have them both non-negative. Okay, so I could pick a point here. Sorry. I could pick a point right here, and I could pick a point right here, and their convex combination is this. Okay, but I could take the lower one and the upper one and multiply them both by some big number and get this point up here. Okay, so this would be a conic combination. But one thing I should say, which is not written here, is if I take all possible conic combinations of points in this set, then I get a convex set. Oops. Okay, so now what we can do is we can take these two different ideas, or we can take different convex sets, and we can start to combine them together. So if I take my half space, which I have, if I just had this one, oops, I don't mean to rub it out. If I just had that one on its own, then this set would be a half space. And so I would have everything on one side of a plane. But if I take my set to be all the x's that are in this half space, and also this one, and also all of these other ones, then I have to be on the correct side of a whole collection of half spaces. And so I could write these down in some matrix form by just lumping together all of the little vectors A into a matrix and lumping together all of the right-hand sides into a vector. Okay, and I get AX less than B. Okay, so I have to interpret now this inequality as being an element-wise inequality. Then what I get is that the first row maybe tells me that I have to be on this side of this plane. And the second row tells me I have to be on this side of the other plane. Okay, and so the intersection, or the region that satisfies both of these things, is just the gray bit. Okay? And so I would describe a set like this as a polyhedron. And then you see sometimes this special terminology that a polytope is just a bounded polyhedron. So a polytope is something that satisfies something like, you would say something like there exists some r greater than 0 such that x is a subset of a ball of radius r, like that. Okay, so it's a polytope basically if I can stick it inside a big enough ball. This one on the left-hand side I cannot put inside a ball because it extends infinitely far to the right. Okay, but the distinction is not really critical between polytope and polyhedron, but we include it just so that you know that there's some kind of difference between the two. So the one on the right is a polytope. I can put a ball around it like that. Okay? Oops. Okay, so now we can also define sets in terms of functions or in terms of level sets of functions. So, I mean, I'm sure that you've all seen a norm. A norm is any function that satisfies these three conditions. Oops. It has to be so the first one says that the function has to be greater than or equal to 0 everywhere, and the only place it's actually allowed to be 0 is at 0. Okay? And also, so this is a positive definiteness condition. The second one says that if you scale the vector by some number, then you scale the result by the absolute value of that number. So this is called homogeneity. And then the last one says that if you add two vectors together, then the function of the sum is less than the sum of the functions. So this one is called the subadditivity property or the triangle inequality. Okay, so if you take the 2 norm, this says that the 2 norm of x plus y is less than the 2 norm of x plus the 2 norm of y, which is telling you something about the lengths of sides of a triangle. Okay, but it's true of any norm. Actually, this is the definition of a norm. And okay, there are many different functions that would satisfy this. And so if we want to be clear about which function we're talking about, then we say x with some symbol in place of this dot. So if I put a 2 there, I mean the Euclidean norm. If I put a 1 there, I mean the 1 norm, and the infinity, I mean the infinity norm. Or maybe some other funny-looking norm. And if I don't put anything there, then that either means that you should know what I'm talking about, or I don't care which norm we're discussing. I just mean any norm. And the one that you should be most familiar with, maybe the only one you've ever seen, is the p norm, which is defined generically for any p bigger than 1 this way. So if I take p as, well, I'll show you on the next slide. I take any p bigger than 1, and I can define this. I can define a function that looks like this, and no matter what p I pick, this is a norm. And you will have seen it probably only ever used with 3 values of p, because I don't think anybody ever uses values other than these 3. I mean, in principle you could, but no one ever does. So if you take p is equal to 2, then you get the square root of the sum of the squares. Okay, so this is the 2 norm. And if you take p is equal to 1, you get the sum of the absolute values of the entries. And if you take the limit as p goes to infinity, what you do is you take every entry, you take the absolute value of every entry, and you pick the biggest one. And we say that this is the infinity norm. And now we can think about what are the sets that are defined by some inequality associated with the level curve of these functions. So say that I take the set of all x's such that x minus some center is less than r, okay, for one of these norms. And just imagine for the moment that xc is 0. So xc is the center of the ball and r is the radius, and the ball that I would get is convex for any norm. But when I say ball here, I mean, when you think of ball, you think of something that's round. The 2 norm ball is round, okay, because the set of all x's that have length in the Euclidean sense less than 1 is this green guy here. That's the 2 norm less than 1. The 1 norm, or the sum of the absolute values, its ball is this diamond shape, okay? And if I take the set of all x's whose biggest entry is less than 1, then I get this outer one, the red one. And if I pick some p in between, if I pick p is equal to, I don't know, 3 over 2, then I get something in between here. And if I pick something bigger than 2 but not infinite, I get something that starts to look like that. Okay, and all of these are convex. If I were to pick p less than 1, then the faces of this would sort of curve in, and I wouldn't have a convex set anymore. Okay, so these are the ones that you'll have seen. There are other norms besides these. Does anybody know of any besides these? No? Okay. You could take, for example, here this is in a sense the sum of the absolute values of all of them. This is the sum of the absolute values of the biggest one. This is why there's just one term there. If I took the sum of the 2 biggest ones, that would be a norm. Or if I picked any number, If I sorted them all and picked the first 5 out of n and added them together, that would be a norm. Okay, why I would want to do that is unclear, but the point is that you can define other functions besides these ones, which are norms. Okay, and now a sort of variation of the 2 norm would be an ellipsoid. So an ellipsoid is one where you take the set of all x's, you give me some center, xc, this is a fixed vector, and I take all the points that have the distance to xc transpose times A inverse times the distance to xc has to be less than 1. And this gives me, if I made this inequality, then I would have some ellipse. I would have some ellipse. I would have the blue curve here. And if I make it an inequality, I get everything inside, which is a convex set. Okay, we didn't prove that it's a convex set, but you can try it yourself and try to prove that it's a convex set. It's not that hard. So, and then I can think about the shape of this set. The shape of the set is determined by the center, and it's determined by the eigenvalues of this matrix A. So if I have all the eigenvalues the same, I get a nice round set. If I have one huge eigenvalue and one small, I get a really elongated set. So these are direction, the vectors pointing towards the wide end and the narrow end. These are the eigenvectors of A. Okay, so this is a nice set. If I had changed this to greater than 1, then I would have everything outside the set, and this is really not very nice. Okay, and then if I want to take the 2 norm ball, then I just set A is equal to r squared times I. So now I have a round set. So this is a variation of the 2 norm. Okay, and this is also a convex set. Now what I can do, so now I have some ingredients. Okay, I have ellipsoids, norm balls, hyperplanes, half spaces, and so on. And now what I can do is I can take my basic ingredients and I can start to add them or combine them together in some way. So the most important one is intersection. So I should think about having some set or some inequality that defines a set, and then I want to ask what happens if I want to be in both sets at the same time, or what happens if I want to satisfy both of these inequalities at the same time. Then I would get for 2 or more sets, the intersection of any number of convex sets is always convex. Okay, this is a really useful property. So we say, okay, you take one set, which is everything to the right of this plane. We take another set, which is everything above, and another set, which is everything down and to the left of this plane. We intersect all of them together, and I get this little triangle, and it's a convex set. And it's easy to prove that this is the case. Okay, and for 2 sets, you do it in the following way. You say, I want to pick 2 points that are in the intersection. Okay, so I call them A and B. I just imagine that I have 2 points which are in the intersection of my 2 sets. Each one of them lies in each of the sets of the intersection. Okay, and then I want to check whether the line between those 2 points is also in all of the sets, because then it would be in the intersection. Well, because each of the sets is convex, then when I take the interpolation between the 2 points, which lies in each set, then that interpolation should lie in each of the sets, and so therefore it lies in the intersection. Okay, so therefore the intersections of sets, convex sets, is convex. And most of the time when we define our convex optimization problems, we write a whole bunch of inequalities. We hope that all of these inequalities define convex sets, and then we're assured that the result is that we have a convex problem, where the intersection of all the things that we defined is also convex. And actually a nice sort of fact is if you have any convex set, you can always write it as the intersection of an infinite number of half spaces. I'm not suggesting that you do that, but you could do that if you wanted to. So you can think of a convex set as being a set which has a bunch of planes that are touching it, or supports. Okay, and if I take the intersection of all of these planes, I get the thing which defines the planes. Okay, so this is maybe the most useful property of convex sets. Now I can take the convex hull of a set. So now suppose that, oops. Yeah. It's really difficult to grab the little arrow. Suppose that I have this set X, and it may or may not be convex, okay? And I take every pair of points in that set, and I take the line between them, and I take all the points that I can generate in this way. So this is the convex hull. So the convex hull of X, of the big set X, is the set of all X's, where I take A and B inside the set, and I draw lines between them, and I take all the lines. Okay? Then I call this the convex hull, and okay, it's called the convex hull because it's a convex set. And I can think of this in a number of ways. I can think of it as being either the set of all points that I can get to by drawing lines between points in my set, or I could think of it as the smallest convex set that holds X inside of it. That's what this says. Or I could say, take all of the convex sets that contain X. Take all of the convex sets that contain X and take their intersection, and that intersection would be the convex hull. That's an alternative definition that's not written there. Okay, and now we should ask, what does this look like? So the one on the left, I have a set which is, okay, it's nice and round over here, and then it has this unfortunate sort of indentation on the bottom surface. And when I take the convex hull, I basically round out that side. So the convex hull includes everything on the line between here and here, which means it includes this blue line. And so this is a way of convexifying a non-convex set. And then likewise, I could take a collection of points. Okay, a collection of points is clearly not convex. I draw all the lines between all of the points, and I can do it with so a convex hull should actually be the set of all combinations of any number of points, not just two. Then I get this gray region. Okay, so again, this is the smallest convex set that contains all of these points. Okay, and so we can write the convex hull like this. It's the combination of all possible points inside the set, convex combinations of points inside the set. And this is a nice operation because if I have a problem which is non-convex, which I said earlier is, in a sense, bad, well, I can sort of fix it up by just making everything convex instead. I won't get the same answer, but, okay, I can get the wrong answer in an easy way, okay, by taking the convex hull. Okay, there's a little bit more to it than that, but for the moment, that's enough. Okay, so now, what aren't you allowed to do? Okay, the thing you're really not allowed to do, and the thing which you always would like to do, is you can't take the union of two sets and get a convex set. So I have here, okay, the red one is a convex set, the blue one is a convex set, and I say instead of being in the intersection, I want to take the set of points that are in either one of these instead of both of them. Okay, and I get this funny looking figure of 8 shape, and this is not a convex set. Okay, so this is bad. Okay, this is not what you want to do if you can avoid it. And this is exactly what happens if you have a decision in an optimization problem where you have a binary variable, and your binary variable says, well, I can either do this or I can do that. And so now this is the set of all decisions that I can make. Then I end up with a non-convex set, and okay, not exactly disaster, but what? Unhappiness. Okay, this is not good. Okay, but there's a warning that you can't take the union, and most things that you would like to do to a convex set don't preserve convexity. Okay, so you can't scale it in a funny way. You can't take unions. There's all kinds of stuff. You can't take holes out of it and so on. So you have to be careful when you have convex sets that you only do operations on them that preserve convexity because you want to end up with a convex problem in the end. Okay, now we could talk also about convex functions. So a convex function is one where you take, you take any 2 points, so you have some function, which is the blue guy here, okay? And you take any 2 points, x and y, any 2 arguments to the function, you evaluate the function at those 2 points. So you get fx and fy. And then you just draw a straight line between those 2 values. Okay, so that would be these values up here. So you take fx, you take fy, and then you just interpolate between those 2 values. You get this line up here. And then you could also interpolate between the two arguments. You could take x and y and draw a line between the two arguments instead of between the two values. And if you do that, if you always end up below this value, down here, then you have what's called a convex function. So this basically says that drawing the straight line between the values always gives you more than actually evaluating the point at the interpolated position between the two values. And we would say that this function is, okay, so this is the definition of a convex function. And we would say that the function is strictly convex if this is a strict inequality instead of a less than or equal to. So this function here is strictly convex because there's always a gap between the blue point and the black point. And that's true for any pair x and y that we would like to pick. Okay, and then we would say that a function is concave if minus the function is convex. So generally speaking, a convex function is one that looks like this, okay, and a concave function is one that looks like that. And so when we talk about convex optimization problems, we're always talking about minimizing things. We want to minimize a convex function. If we want to maximize something, then we should be maximizing a concave function because we can change the sign and make it convex and then minimize it instead of maximize it. Okay, so this is what we would like our objective functions to look like if we're lucky. And okay, so this here is just one definition of convexity, okay? But then we can talk about ways of checking whether a function is convex or not. So if I assume that the function is differentiable, then I can write down a different condition, okay, which is this one right here. And it says that the function is always, if for every x, the function fy is greater than fx plus the gradient times the distance from y to x. Okay, so what does this say? This guy right here says you pick a point x, okay, that's that one. You evaluate the function at that point, you get a number. Okay? Then you differentiate the function at that point, and you get a vector. Okay, this is the gradient. So the gradient is pointing this way. And then I multiply that gradient by the distance that I wander from x. Okay, so this defines a straight line. Okay, this is a linear function of y. So I have here just a straight line. That's this line here. It's a function of y. You have to think of x in this figure as being a fixed point. Then if this function is always below, this linearized function is always below y, then the function is convex. Okay, so this basically says if I linearize the function at any point, I get a lower bound on the function. Okay, so this is an alternative definition of convexity in the case that I actually have a differentiable function. And I can do it in Rn in a similar way by just taking the gradient to be or by taking x to be multivariate and defining the gradient in this way. Okay, so I have here, I can think of this line as being a lower support of my function. Okay, so this is a first order condition for convexity. And okay, it's a necessary and sufficient condition. This IFF is if and only if, okay? And now I can also take a second order condition for convexity, which is that if I differentiate the function twice, and I find that the twice differentiated function is, so this will be a matrix if x is multivariate. If this matrix is positive semi-definite for every x, then the function is a convex function. So we call this guy the Hessian. Okay, it's the matrix that I get by differentiating the function by every combination of variables in the vector x and forming them into a matrix. And I just look at the eigenvalues of this guy, and if all the eigenvalues are always non-negative, then I say I have a convex function. And if all of the eigenvalues are actually positive, then I say I have a strictly convex function. And you should think of this Hessian as being the curvature of the function. So in one dimension, then I would have something like f is equal to x squared. Okay, I differentiate this twice. I get 2. That's the second derivative. Okay, and well, this is always a non-negative number. Okay, so the function is strictly convex. And the number 2 is the curvature of a quadratic function. And if I have a multivariate function, then I want it to be curved in all directions. So I want a function which is bowl-shaped, okay, and the eigenvalues tell me the degree of curvature. And if they're all positive, it's shaped like a bowl. If they're all negative, it's shaped like a dome. And if I have a mix, then the function is curved upward in some directions and downward in others. And this is not what I want. So I have to have positive eigenvalues or non-negative eigenvalues everywhere. Okay, and again, I have to be able to differentiate the function twice in order to do this. Now, this is not to say that the function has to be differentiable to be convex, because if I go back to this figure, this function is not differentiable, but it's a convex function. Okay, because it has no derivative at these 2 points here and here. Okay, but it still satisfies the first definition of convexity. So, and why should we have different definitions? Because if you want to check for convexity, then, well, sometimes it's easier to check one way or the other, but it doesn't really matter. But, you know, if I just give you a function and I say, please check if this function is convex, then the easiest thing to do is start with the definition. Okay? And if that looks horrible or you can't do it, then start differentiating it and see if that makes it any easier. Okay. Oops. Okay, so now maybe you would ask, why is it that we use this word convex to describe functions and then we use the word convex to describe sets, and it's not clear that these things are related at all to each other? Okay, so now I try to show you what is the relationship between the two things. So I take a function f, okay, that's this function right here, this blue line, and I want to define a set, which is the epigraph of this function. So the epigraph says, take all the points x, or all the arguments x, if you like, and form a set which consists of all the x's and all of the numbers t which are bigger than the function evaluated at those points. Okay? And we just define this as the epigraph. So I take this curve. Well, first of all, down here is the domain of f. Okay? Oh, sorry. Sorry. Okay, here we have down here the domain of f. Okay? And then I take the curve fx. It's a convex function. And I take all the points that are above the curve. This is the epigraph. Okay, so the epigraph, if the function is defined in R, because it's a one-dimensional function, then the epigraph is defined in R2. So the epigraph is always one dimension higher than the domain of the function. So you can think of just taking the function maybe in R2 and you just take everything above. And we call this the epigraph. And the function is a convex function, if and only if its epigraph is a convex set. So if everything above a convex function is or if I take everything above a function and I find that I have a convex set, then the function must be convex. Okay, and then we have to be a little bit careful about whether the epigraph is closed or open, but okay, this is not a critical point. Okay, so this is the connection. Convex functions have convex epigraphs, and sets which are epigraphs of things are convex if and only if they are epigraphs of convex functions. Okay, and this is a useful fact, which I'll show you how you can use this in a moment. Okay, so now we can talk about properties of level sets of functions. So I say that the level set L subscript alpha, or the alpha level set of the function f, which I denote L alpha, is just the set of all, it's the set of all x's. It's the set of all x's that achieve the value alpha. Okay, I'll show you a diagram in a minute. And we just call this the level set. So if you like, it's a contour line. When I showed you these figures that have the dotted contour lines of constant value in the function, those contours are level sets. So, okay, if you look on a weather map, you have the lines which are, constant temperature. These are level sets of the function which defines the temperature. And then if I relax this equality to an inequality, then I get what's called a sublevel set. Okay, so a sublevel set would be the set of all x's for which the function is less than alpha. So if I think about the weather map, then if I think about the temperature map, the curve, temperature equal to 10 degrees, the level set would be all of the locations where that temperature is exactly 10 degrees. And then the level set, the sub-level set, would be all the places with worse weather than that, assuming you like warm weather. Okay, so now, so the important thing to remember is that the level sets and the sub-level sets, they're defined in terms of x. They're not defined in terms of the value, okay? So if I take a function, okay, this blue one here, this is not a convex function, okay? Because if I draw a line between here and here, I don't stay below the blue line always, okay? So the function is not a convex function. But if you give me any value, so say you pick this value right here, okay, and I look to see what are all of the points on the curve that have exactly that value, then I get that point and that point. So I should think about this point right here and this point right here. So I should, yeah, okay. I should actually erase this one and this one. Okay, so I take this point and that point, those are the arguments that achieve exactly this blue value right here. That's the level set, okay? Now if I write, what are all the x's that have values below this point, okay? Then I just draw a line like this, okay? And I go down. And so the sub-level set is everything along this line. Okay, it's that segment of the x-axis. That's the sub-level set. And for this function, every sub-level set is a convex set. Okay, so you give me any value, I ask, what are all the arguments that achieve that value? That set of arguments is a convex set. The function is not convex, but in a sense, it's going down monotonically until it gets to some minimum, and then it goes up monotonically, and it doesn't keep changing its mind. That's sort of informal definition of a quasi-convex function. Okay, so this is somewhere in between not convex and convex. Okay, it's a little bit nice, but not very nice. Okay, but mainly I show you this quasi-convex figure not because quasi-convexity is really critical for this course, but to just show you the difference between a level set and a sub-level set. Okay, so now another way of checking whether a function is convex is this way. We say that I pick any line, I pick any 2 points in the domain of the function, okay, and I evaluate the function just along a line. So I can have a multivariate function, but my definition of convexity is I like to think of it as being lines that I draw between points remaining above the curve. So if I just restrict always my function to a line, if the restriction to a line along the domain is convex, then the function is convex, and vice versa. Okay? And so this is a nice way of checking whether the function is convex. So I give you some function f. I claim to you that it's a convex function, and I say, please check if that's true. So what you do is you say, okay, I'm going to pick any x. I'm going to pick any v, okay? And I'm going to take all lines going from x towards v. Okay, so think of t as being a number greater than or equal to 0. So x is the starting point of my line, and v is the direction that I want to move in. And the domain of the function is just how far I can move until x plus tv puts me outside. So now I have a function of just this single scalar parameter t. Okay, and I pick my point, I pick my direction, and I say as I go in that direction, is the function that I get along that line a convex function? Okay, and that's g, and if the answer is yes, then f is also a convex function. Okay, and the nice thing is you can check convexity by checking functions of one variable. So here's an example. This is not the most user-friendly example ever, but if I tell you that my variable is a matrix, a symmetric matrix, x, and I tell you that the domain of this function is the set of positive definite matrices, so ones with positive eigenvalues, then I claim that the log of the determinant of x is a concave function. Okay, it's not obvious that this is true. And it's not obvious how you would check this by using the conventional definition of convexity. And, okay, maybe it's not so easy to differentiate this function either. Okay, so what you can do is you can just do this scalar test. And, okay, I won't do it, but you can take, well, maybe you'll take my word for it that it's not easy, it's less difficult than doing it straight from the definition. Okay, but what I can do is I can form this function gt. I can take log determinant of this scalar valued function now. Now I know how to take the determinant because it's just a scalar. I know how to differentiate and so on. And so the way you do this, I mean, you're welcome to try it if you want, is you have to realize that the determinant of a product is the product of the determinant, and the determinant of a matrix is the product of its eigenvalues. If you know those two things, and you do the second derivative test, then you can prove that this example is true. Or if you can't do it, then you can look in the convex optimization book by Boyd and Vandenberg, and you look for this, you search for log det, and you'll see the proof. It's in there. Okay, but that's, you shouldn't do that. You should try to figure it out. Okay, maybe you give up, then you look in the book. Okay, now, one final thing that I can do to my function is maybe I have a function f which has some restricted domain. So maybe I say f has to be defined on non-negative arguments. Okay, and now I have this funny problem with my implicit domain. I can sort of fix this up by just defining what's called an extended value function. So I take f, okay, and I define a new function f tilde, which is equal to f everywhere in the domain. And outside of the domain, I just say the function is infinite. Okay, so this is, I mean, this is just a trick, really. You just say that if I want to have a function with an unrestricted domain, I just take f and I make the function extremely bad outside of that domain. Okay, and now if I want to minimize over f on a restricted domain, I just minimize over f tilde on an unrestricted domain, and I'm certainly not going to pick anything outside of the domain of the original function because f tilde is infinite there. So this would be a bad idea. Okay, and this doesn't change any of the stuff that we said in the course. It just makes it so that you don't have to have these implicit domain problems everywhere. So it doesn't change the epigraph. The function is convex if it's, sorry, the extended value version of a function is convex if and only if the function is convex and so on. So you will sometimes see this idea of an extended value function. Okay, what time is it supposed to end today? 12:15? 12. 12. 12. Do you want to stop for 5 minutes, or should we just go till 12? 5 minutes. Okay, we stop for 5 minutes. Yeah.
Maybe we can have to continue like 12:15 or something.
I don't mind. What do you? Who agrees?
No, don't break.
Ah. Well, you're outvoted. It's the Swiss system. You're outvoted. Direct democracy. Okay, so we stop just for 5 minutes, and then we'll go till 11:55. Okay, so we said 11:55 we end. Yes? Okay, I believe you. Okay, so now I want to just show you some examples of convex functions, because like with sets, what you want to do is you want to have always available to you some, if you like, library of functions that you know are convex, and then you want to combine them in different ways that you know don't screw up the convexity of the function you end up with. Okay, so I have here just 3 slides of examples of both convex and concave functions. So first of all, these are functions of one variable. So, okay, I mean, I won't prove to you that they're all convex, but just so that you know, any linear function is always a convex function. Okay, affine function is always convex. Okay, this is a very nice one to have. So this is why a linear program turns out to be a convex optimization problem, because it has a linear objective function. Any exponential function is a convex function. Okay, powers of x for non-negative x. Okay, so r plus plus here means the set of x is strictly greater than 0. This is a convex function. Or powers of absolute value and so on. And then we can also say functions that are concave, okay? But concave just means that if I change the sign, it's convex. And so I have, not surprisingly, similar-looking examples. And the one that I want to point out to you is this one, okay, which is not a mistake because it's here, but then it's also here. Because a linear function is the only function that's both convex and concave. So if I think about a linear function, I want to know, is it curving upwards to be convex? The answer is, yeah, sort of. Or it's at least not curving upwards. And is it curving downwards? Well, it's not really not doing that either. It's flat. So it's both convex and concave. Or if you like, I could check that this is convex, and then I could change the sign and check whether it's convex again, and it would still work. Okay, so it's both convex and concave. And some of them have restricted domains. So for example, the log function is concave, but only for non-negative numbers. Okay, so we have here some nice functions that we can use. We can try to assemble our objective functions in convex optimization using these, okay, if we're smart or if we're careful. And these are functions of one variable. Now I have functions of vectors, okay, and you should not be surprised to see that affine functions appear again. An affine function, even in Rn, is both convex and concave. You can check it in the same way. I said before that level sets or balls defined by all the x's that have a value according to some norm less than some number, that makes a convex set. And this is because the functions are convex. Okay, so any norm is a convex function. And it doesn't have to be, as I said, it doesn't have to be one of these p norms. It could be any function that satisfies the three conditions of the norm. Okay? I won't, well, actually, if you look at if you want to prove that any vector norm is a convex function, this is very easy to do because the subadditivity property of the norm looks very much like the definition of convexity. Okay, so if you go to the slide, I won't do it now, but if you go to the slide showing you the definition of a convex function, and then you go to the slide showing you the three conditions defining a norm, pick out the last one, the subadditivity one, I guess also the second one, the homogeneity one. You put those two together, and then you can prove that it's a convex function. It's very easy. It's 2 lines. Okay, but that's left to the reader, as they say in books. Okay, and then we can also have convex functions of things that are not vectors or scalars. We can do convex functions of matrices. So the reason why you keep seeing linear function over and over again is because this is a really important one. So any linear function of a matrix, like the trace of the matrix times some other matrix, would be a convex function of the matrix X. Okay? And also, if I take any norm of a matrix, then this is also a convex function, because the definition of a matrix norm looks just like the definition of a vector norm. So this norm here, the spectral norm or the maximum singular value norm, have you seen that? Yes? No? Okay, you take all the singular values of the matrix, you pick out the biggest one, that's a norm. You can also take any positive definite matrix and add up all the singular values, and that's a norm. Okay, there's lots of different norms for matrices. Okay, so the point of this is not to sort of convince you that these are, important functions or the only convex functions. These are important ones, but just to say to you that when you want to check whether a function is convex, you should try to think about it in terms of these known convex functions, and then try to prove that your function is convex by matching it up with some list of known convex functions, or operations of convex functions that don't screw up the convexity on you. Okay, so now what I'm going to show you is all of the things that you can do to a convex function, not all of them, some of the things that you can do to a convex function and not screw up the convexity. Okay, so convexity preserving operations. So like I said with sets, you can take intersections of sets. This preserves convexity of the sets. You can scale all the sets in a uniform way. This would give you a convex set still. And likewise with functions, we can do the same things. So we should have always available to us some list of stuff that we can do to convex functions and not screw them up. Okay, and so here's 4 examples which we'll discuss. And I don't want to give you the impression these are the only things you can do, so I said many other possibilities, but I don't tell you what any of the other possibilities are. I just tell you that they exist. So if you want to check whether your function is convex, check whether you can use any of these tricks, and then if you can't, then panic and look in the book by Boyd and Vandenberg or the book by what's his name? I've forgotten. Anyway, find any Bertzakis or Rockefeller. You look at any convex optimization book, and you hope that you've not done something sinister to your function to mess it up. Okay, so but these are the most important ones by far. So, right. So one thing I can do is I can take my convex function or any combination of convex functions, and I can multiply them by non-negative numbers and add them together, and I get a convex function. So if f is a convex function, 2f is a convex function. And f and g are convex functions, then f plus g is a convex function. So taking non-negative sums of things preserves convexity, and you can prove this. Okay, it's not proven here. You can prove it just using the direct definition of convexity. Okay, and I should point out to you that the main thing is don't multiply it by a negative number, because if you multiply it by a negative number, you're going to end up with a concave function and not a convex one. Okay, which is usually bad. Okay, so this means that we can mix and match our functions to some extent by adding together different standard types. Or if we take the argument, so the second one, the composition, says I have a function f, which is convex. Okay, so f of y is convex. Then I can put in any linear function inside. So I can say y is equal to ax plus b, and then have f of y. Okay, and then I should ask, is this guy, which is now a function of f, is that a convex function? Okay, and the answer is yes, it is. So if I have a norm, any norm, which I usually write as the norm of x, the norm of ax minus b, also convex. The norm is convex, so I put a linear thing inside its argument. I didn't screw it up. Okay, so this is another nice one. And then I can take the pointwise maximum of some functions. Okay, so I give you a collection of functions, f1 through fm, and I define a new one, which is just the biggest value at x is the biggest value of each one of those at x. Okay, and I claim to you that this is a convex function. Okay, and an example is if all of the functions are linear, then I get a convex function. Now, this one maybe is not so clear, so I try to draw you a picture. Okay, so so I have here some functions in two variables. So here's one function. Here's another function. All of these functions are convex. Here's a third one. Here's a fourth one. Okay, these are four different functions. And now I take, I'm going to get really fancy now and use a different color. Now I take this is x. At every point x, I just take as the value of my new function the biggest of these. Okay, so that would be here, and then here, and here, and here. Okay, so that's the pointwise max of these functions. The pointwise max is also convex. Okay, assuming I'd drawn nice, tidy curves, which I didn't. Okay, but the pointwise max is convex. And how would you prove this? Well, you can do it in two different ways. One way would be to just, again, check directly the definition of convexity. Okay, this is one way. Or another really tricky way is to say that every single one of these functions has a convex epigraph. Okay, this is the definition of a convex function. And then I should ask, what is the epigraph of the max of these functions? Okay, the epigraph of the max of these functions is the intersection of the epigraphs of the functions that I started with. And since all of the epigraphs are convex sets, their intersection is convex, and so the max is a convex function. Okay, so this is sort of trying to convince you that this connection between convex functions and convex sets through the epigraph is useful. Okay, but if you don't like that definition, then you can, or you don't like that proof, then you can just do it directly from the definition. Okay, now this one, there's a sort of subtle difference between, There's a subtle difference between this one and the next one I'm going to show you. So this one says you take any collection of functions and you take the pointwise max of those functions. So I wrote down 4 curves, or I wrote down a finite number of curves. So this is pointwise max. Now I could also take an infinite collection of curves, and I would get the same result. Except now, because I have an infinite number of things, I can't really write max anymore. I have to write soup instead. Okay, but it's basically the same idea. So I have a function of two variables. So I think of fxy as parameterizing a collection of curves or functions where y is the parameter. Okay, so you pick any y, and the function fx for that particular y is a convex function. Fxy together doesn't have to be convex. You just pick y, and that produces for you a convex function. And I have maybe an infinite number of these y's. So I have an infinite number of curves. And then I take, for every x, the worst case over all the y's. And I would have a figure like I had before, except it would take me a long time to draw because I have an infinite number of curves. Okay? But it's the same idea, and the proof is basically the same, that this function, gx, should also be a convex function. Now, this becomes useful when you want to define a function like this guy. This is the support function. And I won't talk about the other two, but the support function I'll show you. So the support function says you give me a set A, okay, and I want to define a convex function using this set. Okay, so I do it in so what I do is I take the argument that you gave me x, and I take the dot product of x with every y in the set, and I take the biggest dot product. Okay, and then I claim that this is a convex function. And I will try to show you what this looks like. So this looks like this. And it doesn't matter, actually, if this set is convex or not. So, okay, so, no, I don't want to black. Okay, so I have some axes like this. And now I'm going to draw for you a non-convex shape. And for some reason, when you read books on convex optimization, the classic non-convex shape looks like this. All the examples have this bean shape. I have no idea why, okay? But it's always that shape. Okay, so this is a non-convex set. Now, what I do is I want to define the support function of this set. So this set is called A. Okay? And now I pick any point x. Okay, so here's a point x. Here. Okay? And it has some... So it's a vector, okay, pointing to that point. And now what I do is I take the dot product of this vector with every vector inside the set, okay? And I try to make this dot product as big as possible, okay? Which means that I should pick a point which is on the boundary of the set and which aligns itself to the greatest degree possible with this dotted line, okay? So I would find that that point is right here. Can you see? Yep. Okay, so, I mean, I claim just from looking at the figure that this appears to be at least the vector that has the greatest dot product with x. Okay, so this is y star in that maximization problem. And then the dot product of x with y is the value of the support function. Okay, and what it defines for me, I can think of it in the following way. I take this vector x to be the normal to some plane, okay, and then I try to, I try to push this plane, I should try to align the plane such that the normal of the plane is pointing towards x, and then I push it down towards the set until it just touches this point y, and that would be the maximizer in that problem. Okay, and it turns out that if I define a function of x in this way, then I get a convex function. Okay, but you see the support function appearing a lot in optimization problems and in control problems. Okay, can I take this away? Okay. But the proof of of convexity of this function is just, okay, I have a whole bunch of functions, I take the max of all the functions, and I get a convex function again. In the same way that I did for a finite number of points. Okay, and I can do it likewise for other functions which involve maximization over parameterized families of functions. Okay, so this is what we call a convexity preserving operation. I didn't screw up the convexity by doing this. And then another one that I can think about, and this is a really important one for control, is if I take a function which is actually convex in both x and y, and I minimize partially over some convex domain, then the new function that I get is also convex. Okay, so this says that suppose f is a function of two variables, and I fix x, and I minimize over y. Shouldn't be drinking so early in the morning. Okay, anyway, so you have a function of two variables. It's convex in both. Okay, you fix x, and you minimize over y, and you take that minimum value as the value of g of x. And you do this for every x. Then you would find that g is also a convex function. Okay? Is that clear? Okay, and you will see this in the control part because y will be the control variables that you pick. Okay, so and x will be the state that you find yourself in. Okay, so you say, I have an initial state x. Okay, I choose the optimal input sequence for that state. And then I want to think about what is the value of this problem that I'm solving as a function of x. And you will find that this is a convex function. Okay? And you will find in the control part, I realize this probably doesn't make sense now, but you will find in the control part that if you take y to be the inputs and x to be the initial state of your system, then g will turn out to be a Lyapunov function for your problem. Okay? But you'll see that in more detail later. Okay, now the other thing I can do is I can try to combine my functions together. Okay, this is called composition. So if I have scalar functions, and if g and h are both convex functions, and h is, so h here it says h tilde because this is the extended value version of the function. So it basically says that if I take a convex function g, and I stick it inside another convex and non-decreasing function h, I maintain convexity. Or likewise, if g is concave, and I put it into a non-increasing function, then I maintain convexity. Okay, so if I find that I have some horrible-looking combination of two different convex functions, I should remember this rule, and I should check whether I have actually screwed up convexity or not. Because it's generally not the case that you can just combine convex functions in arbitrary ways. Okay, but this is one way that you can. Okay, so this is for scalar functions, and then likewise there's a similar rule for vector-valued functions. And the vector-valued function just basically says, as long as you apply the rule from the scalar case, element-wise to every component of your function, then everything is okay. So the h, which is the outer part here, it just has to be non-decreasing in each argument. So g would be a function mapping Rn into some new, maybe different sized vector, okay? And this has to be a convex function in each component, and then each component of h has to also behave itself along the lines of the scalar case rule. So basically, this is not any different from the scalar case, okay? And it just says that you're allowed to combine convex functions in certain ways and not screw up the convexity. Okay, so this is just something to bear in mind. So usually what happens is you model your problem as an optimization problem in some way, and then you say, oh, is it convex? Well, not really. Maybe I should look and see if there's some rules I can apply. And you desperately hope that you can prove that it's convex using some combination of these rules. And if not, you hope you can manipulate it in some way to make it so. Okay, so maybe now just very briefly, we'll start on the convex optimization part, and then we'll finish it tomorrow. Okay, so what did we do? We had at the beginning, we said an optimization problem is one where I have some constraints. I have a function I want to minimize over some variables, and it may or may not be nice. I hope it's nice. Probably it won't be, though. And I have a bunch of functions defining the constraints and the objective function. And then I said, well, let's talk about convex sets, which we can think of as convex constraints. And let's talk about functions that are convex. And now what we want to do to get a convex optimization problem, we just want to make an optimization problem composed entirely out of these two parts. Okay, so if I make an optimization problem and every bit of it is convex, I have a convex optimization problem. And this is generally good. Not always, but generally it's a good thing. So I think we'll just do 4.1. So, right, so now I had right at the beginning, I had this, what was advertised to you as a standard nonlinear optimization problem, which was to minimize some function. I didn't say what kind of function it was, subject to satisfying some inequalities, and subject to satisfying some equalities. And at the beginning, I had here, instead of a linear function, I had just some function h. Okay, it just said hi of x equal to 0. And so hi of x equal to 0 could be, in general, some curvy-looking surface. Okay, but now I want a convex problem. And a convex problem is one that looks like this, in this standard form, where f has to be a convex function. The domain of f has to be a convex set. Every one of these inequalities has to have a convex function on the left-hand side. And by the way, I should say that sometimes people get very confused because they say, well, I have f of x less than 1. And what do I do because it's not less than 0? Well, you define a new function f minus 1 less than 0. Okay, this is, so you can put everything onto the left-hand side and call that your function. Okay, so this has to be a convex function. And then the equalities have to be linear equalities or affine sets. Okay, if you put anything other than an affine set here, this is not going to be a convex problem anymore. And the reason is that the domain of your function will have some curvy component to it, the surface of a curvy set. And this will not be convex. So we take here always linear equalities when we want a convex problem. And if you like, the reason why this works is you can actually get rid of all the equalities by saying that here aix has to be less than b, and aix has to be greater than b, which means that this function on the left has to be both convex and concave. And the only time that works is when the function is linear. Okay, so that's why this last guy has to be linear. And if I have all of the ingredients of my problem satisfying all of these conditions, then I have a convex problem, and usually this is nice, and usually I can solve the problem. Okay, so let's see what we... Okay, so now what I can do is I can take this, this problem here, and in the second case, I just wrote down p different linear constraints. Okay, another way of writing the same problem is to say I have the same objective, I have the same inequalities, and I just gather together all of the equalities into some matrix vector product equal to all the right-hand sides. Okay, but this is exactly the same as the problem description on the previous slide. It's just that I've written all of the equality constraints jointly. And so this is a plane, or a hyperplane. So I have here a problem where I minimize a function subject to being inside some region defined by convex inequalities. So this will be a convex set. And then here I pass a plane through the middle of it, and then those are the x's that I'm allowed to use. All right, so now maybe I'll do this slide and then the next slide, and then we'll stop. So why should you care about this? You should care about this because of this theorem, which says that if you have a convex optimization problem, every locally optimal solution is globally optimal. Okay, so this helps you because suppose that you take this, even forget about the constraints. Suppose I give you a function, I say, please minimize this function. Okay, so you say, well, I'm going to minimize my function, so maybe the smart thing to do is to go downhill. I keep going downhill until I can't go downhill anymore. And I say, well, I'm at a locally optimal point because every direction is going uphill. Then if the function is just a function, a nonlinear function, you have no idea if this point is any good or not. You just know that if you move a little bit, it's not going to get any better. Maybe way over there, there's a better solution, but near the point that you've converged to is locally optimal. For a convex problem or a convex function, if you go downhill and you reach a point where you can't improve, then that is the best answer. Okay, and so this means that you should no longer have to worry about whether your downhill search is actually any good, because if you hit the bottom, then you're not going to get any better than that. So this is nice because it's very easy to check whether the solution you get is actually a globally optimal solution or not. This is one of the reasons why it's nice. Okay, and then I have down here a kind of cryptic warning, okay, which says that writing an optimization problem like this is not that easy. Okay, sometimes it's easy for me to say, please minimize the distance to a box, from this point to a box, and then you write it down and it's a convex problem. But that's because I intentionally picked one that was easy. A lot of the time what happens is that you have some optimization problem, which is, please minimize the drag on this surface subject to, the mass not being more than some number. It's not that nice of a problem description, and it's not always clear that you can write the problem in this form, that you can compose it entirely of convex functions. And when I say tricky, what I mean is that maybe the problem that I've given to you in its kind of natural state isn't a convex problem. But what you can do is maybe you can do a change of variables, maybe you can add some variables, you do some substitutions, you do some scaling or other transformation. You keep working at it, bashing it until eventually, you hope, you can make it look like this. This is not always possible, but it's always worth the effort, because if you can make your problem a convex one, then you're in a good place. If you can't make it a convex one, okay, I mean, it's an overstatement, but you're usually in a bad place. So if you've seen, how many of you have seen the Euler parameterization in control? You seen this? Yeah? Okay, so the Euler parameterization says something like, I want to find a controller that's stabilizing in feedback with some plant. Okay, so I write down the set of all controllers which stabilize my plant. And this is not a convex set. And so if I say find the best one, then you can't do it. But you do some extremely tricky change of variables, and suddenly, like magic, you get a convex problem. You solve it, and then you change the variables back, and you get the right answer. And this is like magic, okay? I mean, it's amazing. And it's not even that hard, okay? But it's just, you're like, wow, that's, how did Euler think of that? I don't know. You have to ask him, I guess. But anyway, but so, and this happens a lot. So if you take the robust control course, you'll see that there's a lot of work that goes into making problems look this way. Okay, but we're in the fortunate condition that when we do the MPC course, the optimal control problems kind of naturally look like this. Okay, so now I just show you this one last slide, which is to try to convince you why this is the case. So I claim my theorem. For every convex problem, every locally optimal solution is globally optimal. And I can prove it in the following way. Take X and assume that X is locally optimal, okay, but not globally optimal. And suppose that I had a convex function, okay? So I somehow assume the contrary to the theorem. I say X is locally optimal, but it's not the globally optimal point. So because it's not globally optimal, there must be somewhere that's better. Okay, so let's call that point Y. Okay, and Y must have a value better than X. Okay, otherwise it wouldn't be globally optimal. And so now I draw a little figure. Oh, no, sorry. Then I say, well, X is locally optimal if it's at least better than all the points near it. Okay, which means that X is less than or equal to, Fx is less than or equal to Fz if I don't go too far from X. So what that means is that I have here the function f, and I take it around fx. Fx is the locally optimal point. So the function around it is either curving upwards or it's at worst flat, okay, because it's locally optimal. But then somewhere far away, more than r distance away, there's this other point y down here. I should have written a y right here. And it has a value fy which is lower, okay? And now I check, is it possible to have a convex function which, is it possible to have a convex function which has that value there and this value here and something higher or at least not better than fx in between? And the answer is no, because this would violate the definition of convexity. Okay, so therefore I have a contradiction, and so my assumption that the theorem is wrong is itself wrong. Okay, so this is the way I prove it. All right, so now I'll stop now. So tomorrow what we'll do is we'll talk a little bit about how to check whether a function is optimal, and then we'll talk about duality and why problems are easy to solve. Okay, so thank you.